Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you. Relativity made simple. Unlocking the secrets of time, space, and the universe. The theory of relativity, developed by Albert Einstein, is one of the most groundbreaking concepts in physics, fundamentally changing how we understand space, time, and the universe. At its core, it challenges our everyday perceptions and reveals that the universe doesn't always behave the way we expect. To grasp relativity, it's helpful to imagine it as a way of understanding how objects move and interact in different situations, particularly when they approach the speed of light or exist in strong gravitational fields. It's not an easy concept at first, but with simple explanations and examples, its beauty begins to unfold. Start with the idea of time. We often think of time as a constant, something that ticks away at the same rate for everyone, everywhere. However, Einstein's theory shows that time is not absolute. It can stretch or compress depending on how fast you're moving or the strength of the gravity around you. This phenomenon is called time dilation. Imagine two twins. One stays on Earth, and the other travels to a distant star at near the speed of light. When the traveling twin returns, they will have aged less than their sibling who stayed behind. This isn't science fiction, it's a real effect, demonstrated with highly accurate atomic clocks flown on airplanes. The faster you move, the slower time passes for you relative to someone who isn't moving. Now consider space. In everyday life, we think of space as a rigid framework where objects exist and move. But relativity shows that space, like time, is flexible and can be warped. Picture a trampoline with a heavy ball placed in the middle. The surface of the trampoline bends around the ball, creating a dip. Now, imagine rolling a smaller ball across the surface. Instead of moving in a straight line, it curves toward the heavier ball, as though drawn by an invisible force. This is an analogy for how gravity works in Einstein's theory. Massive objects like planets and stars warp the fabric of space and time, and this curvature guides the motion of other objects. What we perceive as gravity is actually the effect of this warping. A classic example of this is how light from distant stars bends as it passes near the sun. During a solar eclipse in 1919, scientists observed that stars appearing close to the sun in the sky seemed slightly displaced from their usual positions. This wasn't because the stars had moved, but because the sun's mass had bent the path of their light. This observation provided one of the first major confirmations of Einstein's theory and astonished the scientific community. It showed that even light, which we typically think of as traveling in straight lines, follows the curves in spacetime created by gravity. Relativity also changes how we think about energy and mass. Einstein's famous equation, E equals mc squared, states that energy, E, and mass, m, are interchangeable, connected by the speed of light squared, c superscript 2. This equation explains how a small amount of mass can be converted into a tremendous amount of energy, which is the principle behind nuclear power and atomic bombs. For example, when a tiny fraction of the mass in a uranium atom is converted to energy during a nuclear reaction, it produces an explosion of immense force. This insight revolutionized physics and opened the door to understanding the processes powering the stars, where hydrogen atoms fuse into helium and release vast amounts of energy. Another fascinating aspect of relativity is the idea that there's no single, universal perspective. Imagine you're on a train moving at a constant speed, and you throw a ball straight up in the air. From your perspective, the ball goes up and comes straight back down into your hand. But to someone standing on the ground watching the train pass by, the ball traces a curved path, because it's moving both upward and forward with the train. Both observations are correct. They're just different perspectives of the same event. Relativity extends this concept to show that measurements of time, space, and even simultaneity depend on the observer's motion. Events that seem simultaneous to one observer might not be simultaneous to another moving at a different speed. These ideas may seem strange, but they've been confirmed through countless experiments and practical applications. GPS satellites, for instance, rely on corrections based on relativity to function accurately. These satellites orbit the Earth at high speeds and experience weaker gravity than we do on the surface, causing their clocks to tick faster than those on the ground. If engineers didn't account for this, GPS devices would quickly become inaccurate, with location errors accumulating at a rate of kilometers per day. The theory of relativity challenges us to think differently about reality, revealing a universe far more interconnected and dynamic than we ever imagined. It shows that time and space are not rigid backdrops but active participants in the cosmic dance, constantly shaped by motion and gravity. While these ideas can seem counterintuitive at first, they are supported by evidence and have transformed how we explore the universe, from the behavior of particles to the motion of galaxies. Relativity teaches us to look beyond appearances and discover the deeper truths hidden within the fabric of existence. To truly grasp the impact of Einstein's theory of relativity, it's important to explore its two key parts: special relativity and general relativity. Each builds on fundamental principles but applies them in distinct ways. Special relativity focuses on objects moving at constant speeds, especially close to the speed of light, while general relativity addresses gravity and its effects on spacetime. Both parts challenge our intuition, but examples from everyday scenarios can make these abstract concepts easier to understand. Special relativity is rooted in one revolutionary idea: the speed of light is constant and unchanging, no matter how fast you're moving or where you're observing it from. Imagine you're on a train traveling at 60 miles per hour, and you throw a ball forward at 20 miles per hour. To someone standing still outside the train, the ball appears to be moving at 80 miles per hour, 60 plus 20. This is how motion normally works. But light doesn't behave this way. If you shine a flashlight while moving at half the speed of light, the beam of light still travels at the same speed, 186,000 miles per second, no matter who's measuring it. This constancy of light's speed has profound consequences for time and space. One consequence is time dilation. Let's imagine two friends, Alex and Jamie. Alex boards a spaceship capable of traveling near the speed of light, while Jamie stays on Earth. As Alex zooms through space, time for them slows down relative to Jamie's perspective. If Alex spends what feels like a year traveling, they might return to find that decades have passed for Jamie on Earth. This isn't a trick of perception but a physical reality. Time itself stretches for Alex because of their high speed. Astronauts aboard the International Space Station experience a tiny version of this because they're moving faster than people on Earth. But the effect is minuscule compared to speeds close to light. Length contraction is another surprising result. When objects move at speeds close to the speed of light, they actually shrink in the direction of motion, at least from the perspective of an outside observer. For example, if a spaceship were traveling past Earth at near light speed, someone on the ground would measure the spaceship as being shorter than it appears to the astronauts inside it. This isn't just an illusion, it's a measurable effect of high-speed travel. These phenomena reveal how deeply intertwined time and space are, behaving in ways we don't notice in our everyday experiences at slower speeds. General relativity takes these concepts further by introducing gravity as a fundamental player in the fabric of spacetime. Before Einstein, gravity was understood as a force pulling objects together, as described by Isaac Newton. However, Einstein proposed that gravity is not a force at all but the result of massive objects bending spacetime. Imagine placing a heavy bowling ball on a stretched rubber sheet. The ball creates a dip in the sheet, and if you roll a smaller ball nearby, it will spiral toward the heavier ball, as though pulled by gravity. This bending of spacetime explains why planets orbit the Sun and why objects fall toward Earth. One dramatic example of this is the way light behaves in strong gravitational fields. Light, which always travels in a straight line through flat spacetime, can be bent when passing near massive objects like stars or black holes. This effect, known as gravitational lensing, allows astronomers to see distant galaxies that would otherwise be hidden behind other objects. The warped spacetime around a massive galaxy cluster acts like a magnifying glass, bending light and creating distorted images of the galaxies beyond. These cosmic phenomena not only confirm Einstein's predictions but also provide a tool for studying the farthest reaches of the universe. Another fascinating prediction of general relativity is the existence of black holes, regions of spacetime where gravity is so intense that nothing, not even light, can escape. Black holes form when massive stars collapse under their own gravity, compressing their mass into an incredibly small space. At their core is a singularity, a point where spacetime is infinitely curved. The boundary around a black hole, known as the event horizon, marks the point of no return. Anything crossing this boundary is lost to the black hole forever. Observations of stars and gas orbiting these invisible giants have provided compelling evidence for their existence, and recent images of black holes captured by telescopes have brought these mysterious objects into sharper focus. General relativity also predicts that massive objects in motion can create ripples in spacetime called gravitational waves. These waves spread outward like ripples in a pond, carrying information about their source. In 2015, scientists detected gravitational waves for the first time, produced by the collision of two black holes billions of light years away. This discovery was a landmark moment, confirming one of Einstein's boldest predictions and opening a new window into the universe. Gravitational waves allow us to listen to cosmic events that were previously invisible, such as black hole mergers and neutron star collisions. These effects of relativity, time dilation, length contraction, space-time curvature, and gravitational waves may seem far removed from daily life, but their implications are profound. They reveal a universe that is dynamic and interconnected, where time, space, and gravity are not fixed and rigid but flexible and fluid. These insights have not only transformed our understanding of the cosmos but also laid the foundation for technologies like GPS, which relies on corrections for time dilation caused by both speed and gravity. By bridging the gap between the abstract and the tangible, relativity continues to expand the boundaries of human knowledge. The theory of relativity doesn't just reside in the realm of scientific experiments or theoretical equations. It has profound implications for how we understand the universe and our place within it. At its heart, relativity reveals a cosmos where time and space are not fixed but interconnected and dynamic, constantly shaped by motion, energy, and gravity. This reshaping of fundamental concepts extends to some of the most awe-inspiring phenomena in existence, offering a lens through which we can grasp the extraordinary complexity of reality. One of the most fascinating predictions of relativity is the possibility of time travel. While the idea may seem like science fiction, the mathematics of relativity allows for scenarios where time operates in unexpected ways. Time dilation, for example, already demonstrates that high-speed travel can cause time to pass more slowly for a traveler relative to someone stationary. In theory, if a spaceship could reach speeds close to the speed of light, its crew could effectively leap into the future by experiencing time much more slowly than the rest of the universe. Although practical limitations, such as energy requirements, make this impossible with current technology, the concept itself is grounded in the principles of special relativity. Black holes, predicted by general relativity, take the relationship between space and time to extreme limits. Near the event horizon of a black hole, time slows dramatically for an outside observer. If a spaceship approached this boundary, an observer far away would see the ship's clock tick more and more slowly as it neared the event horizon. To the crew inside, however, time would appear to move normally. This warping of time leads to intriguing possibilities about the nature of reality near black holes, including the theoretical existence of wormholes. Wormholes are hypothetical shortcuts through spacetime, connecting distant points in the universe. While they remain speculative, they are a natural extension of Einstein's equations, offering tantalizing ideas about interstellar travel or even connections to other universes. On a cosmic scale, relativity helps us understand the origins and fate of the universe itself. The general theory describes how massive objects like stars and galaxies interact with spacetime, influencing everything from the formation of cosmic structures to the movement of distant galaxies. Observations of the universe reveal that it is expanding, with galaxies moving away from each other over time. This discovery, tied to Einstein's equations, led to the concept of the Big Bang, the idea that the universe began as a singular point of immense density and has been expanding ever since. General relativity provides the mathematical framework for exploring this expansion and predicting the universe's future, whether it will continue to expand indefinitely, slow down, or collapse back in on itself. The interplay between relativity and quantum mechanics, the physics of the very small, is another area of profound curiosity. While relativity explains gravity and the large-scale structure of the universe, quantum mechanics governs particles and forces on the tiniest scales. These two theories, however, do not easily align. Relativity breaks down when applied to quantum scales, such as inside a black hole or at the moment of the Big Bang. Scientists are working to develop a unified theory, often referred to as quantum gravity, to reconcile these differences. Concepts like string theory and loop quantum gravity aim to bridge the gap, but the search for a complete understanding remains one of the biggest challenges in physics. Relativity also shapes our perception of the cosmos in ways that reach beyond science and into philosophy. It forces us to rethink notions of absolute time and space, replacing them with a universe where reality depends on perspective. For instance, the idea that two events happening at the same time for one observer might not be simultaneous for another challenges the idea of a universal now. This relativity of simultaneity suggests that our experience of time is deeply personal, shaped by our motion and position in the universe. Such ideas inspire profound questions about the nature of existence, consciousness, and the interconnectedness of all things. Even though the equations of relativity can seem abstract, the theory has practical implications that touch our daily lives. Technologies like GPS rely on relativity to function. Satellites orbiting Earth experience both time dilation from their speed and gravitational time shifts due to being farther from the planet's surface. Without accounting for these effects, GPS systems would quickly become inaccurate, causing errors in navigation that could affect everything from smartphones to aircraft. Similarly, the understanding of energy and mass provided by E equals mc squared underpins advancements in fields ranging from medical imaging to renewable energy. The legacy of relativity extends far beyond its scientific achievements. It represents a triumph of human curiosity and creativity, showing how abstract thought can lead to profound discoveries about the universe. Einstein's work continues to inspire generations of scientists, encouraging them to push the boundaries of what is known and explore the mysteries of existence. The principles of relativity remind us that the universe is not as static or simple as it seems, but is instead a dynamic, interconnected web of time, space, energy, and matter. In the end, relativity invites us to see the cosmos in a new light, not as a fixed and predictable machine but as a living, evolving entity governed by principles that challenge and expand our understanding. It teaches us that the universe is far more mysterious and wondrous than we ever imagined, and that our journey to uncover its secrets is far from over. Through relativity, we glimpse a reality that is at once strange and beautiful, a reminder of the boundless potential of human thought and exploration.